My name is Alok. I'm from Veritas, part of the Symantec, and today I'm going to talk about data modeling in Cassandra. We have been using Cassandra for about 2 years now, so this presentation is mainly to share some of our experiences with regards to data modeling in Cassandra. There were certain things that we learned easy way, but obviously there were some things that we learned the hard way. We didn't get it right first time, but we learned from it. So basically sharing some of those experiences with you guys. So this is the agenda for presentation. I'll start with a brief product overview. Then I'll talk about summarization, which is the main use case where we had some of the key data modeling challenges. So I'll talk about what exactly it means in context of our application and what issues, what challenges we had, how did we solve it. And then we'll dwell into the details of schema of a specific column family. We call it intermediate summary. So this is the column family that helps us achieve this summarization use case. So I will talk about again what were the challenges, how did we solve those challenges, and basically how the schema evolved based on our learnings. So to start with the product overview, the information map is the web interface for our application. It's a multi-tenant Veritas managed cloud service, and the idea is to allow our customers to get better insight into their data. So basically help our customers manage their data more efficiently. And to achieve that, what we do is we collect metadata for various objects. These objects are the files on various file servers. These file servers could be spread across different geographical locations throughout the world in different data centers. And the users of this information map, they can then do various kinds of queries on that data to get more stats about their data. So basically they can use various filter combinations through which they can slice and dice the data and drill into specific entities, and by that they can get some more insights into that data. So this is how the information map dashboard looks like when our customer logs into information map. And as you can see on the word map view, there are some circles. So basically they are showing the total amount of data stored in those geographical locations. And on the top left hand side, you've got distribution of data by locations. So top 15 locations by size, then you have got top owners by size. On the other side, you have got distribution of data by content sources. So content source in our application is referring to actually file servers for which we are collecting metadata. And then you have got distribution by shares. So top shares by size, and at the bottom you have got distribution by item type. So item type is basically what type of file it is. Is it a office document, is it CAD, video, engineering file, those kind of things. And then at the bottom you have got age categories based on created, modified, access, age. So items are grouped based on these age categories. So the customers can say, okay, how much data was created in last week, last month, or how much was accessed in last 6 months, those kind of things. And then you have got file size categories. So basically grouping data into file categories, file size categories. For example, how much belongs to up to 10 KB, how much is between 10 to 100 KB, 100 to 1 meg, and so on and so on. And at the bottom you have got various filters, and using those filters, actually these filters corresponds to all those things I talked about, like item type, share, content sources, file size, age categories, all those things. And using those filters, customers can drill, they can do various combinations, they can choose various combinations of those filters, any combination of the filter, and they can drill further and get stats about those filter combinations and drill it to specific entities. So this slide just gives you an overview of what our production cluster looks like. It's a 18 node cluster hosted in Amazon then some of the specs of the cluster nodes. And then in terms of Cassandra cluster usage stats, we have got about 5 billion items stored in the production cluster. It's an average of about 300 million items per customer. And the largest customer is close to now 2 billion items, 1.9 billion items. In terms of the data usage of Cassandra, we have got about 7 terabytes of data across the entire cluster, which is 380 to 410 gigabytes per node. And this slide is just giving you a typical cluster usage. So average CPU across all the nodes, average IO across all the nodes. Okay, so let's talk about summarization in context of our application. So to start with, what exactly is summarization in context of our application, and first of all, why do we even need it? So as I showed earlier on the information map, our customers would like to get stats about their data, and for that they will do various kind of queries using various filter combinations, and they want to basically drill into it and get better insight. And all those queries needs to be interactive. So we aim for less than 5-second response time for these queries. And given that we are dealing with potentially billions of items, obviously we cannot take the naive approach of indexing all those items and then doing queries across all those billion items and then trying to get stats on the fly, aggregations on the fly. So that's simply not going to work, that will not scale. So obviously we need something in between. And the way we do it, we create pre-aggregated view of that data using certain known combinations and known ranges. And then we use that pre-aggregated view to drive the queries from our information map. So through this pre-aggregated view, based on the queries from the information map, we do further aggregations, and hence this pre-aggregated view is what we call summary. And the process of creating this pre-aggregated view and keeping it up to date with the data, the new data that we are getting and all those things is our summarization process. So in context of our application workflow, there are 2 stages of summarization. Obviously the first box represents the first stage, and then the second box represents the second stage. So to start with, we have something we call agents. These agents are responsible for collecting metadata from various file servers for the files on those file servers. And then they push this metadata to us through cloud, and then we will store the information in Cassandra. And as far as this presentation is concerned, there are 2 key tables. One we call item metadata and the other one we call intermediate summary. So this first part where we are storing the information into Cassandra is what we call ingest part of our workflow. And in this ingest part, we will store this information first in the item metadata. So here we will have one record for every metadata item that our agents have seen and provided us with. So for example, if a customer has got, let's say 2 billion items, then in this particular table for that customer, we will have 2 billion entries. Then while inserting into item metadata, we will also insert into another table, another column family, we call it intermediate summary. And the idea is, by virtue of its schema, we will be grouping items into different bucket combinations. These buckets are the facets that I showed on the information map earlier, like item type, age category, age buckets, size, those kind of things, owner buckets. So the idea is to group all the items that belong to a given bucket combination using the schema of this intermediate summary. So this is basically our first stage of the summarization. So just by virtue of its schema, when an item is inserted in this intermediate summary table, it gets grouped into a specific bucket. So the items belonging to the same buckets are grouped together. Then what we have is our daily transformation process that walks through all the items in the intermediate summary table. It does some more aggregation, it does some transformations, and then it pushes this further aggregated transformed data to Elasticsearch in an index. So basically, if you look at the workflow, we start with billions of items in item metadata table, and through first stage summarization, now we have got hundreds of millions of rows in intermediate summary table, And as part of our daily transformation, which is our ETL process, which is extracting from Cassandra, doing some transformation, pushing it into Elasticsearch. So as part of that ETL process, now we end up with tens of millions of items in Elasticsearch index. So now this Elasticsearch index is what drives the queries on our information map. So now as you can see, now we have reduced the search space from billions to tens of millions of items in the Elasticsearch, and that's how we could do all those flexible queries in less than 5 seconds, and we can get less than 5 second response time. So here I've got an example just to show in an easy way how that two-stage summarization is taking place. So let's say agents have seen 5 files. So I've got metadata for those 5 file objects. They will translate into 5 rows in item metadata table in Cassandra. And in this example, I've got only 2 buckets, the date bucket, which is weekly bucket, and the file type bucket. So while inserting into intermediate summary, because of this grouping into different buckets, we'll end up with 3 rows. So this weekly bucket in this example is calculated from 1st January 2015. So the idea is to calculate this bucket from a fixed date in past. So you can see that 2 items belong to weekly bucket number 37 for file type Word. Then 2 other items belong to weekly bucket number 2 and file type Excel. And only 1 items belong to weekly bucket number 7 and file type Excel. So now from 5 we are to 3. And then our ETL process will run, our daily transformation process will run on this middle table, and it will convert these 3 rows into 2 rows in Elasticsearch index. So the main transformation that takes place here is that date buckets, the weekly buckets, get converted into what we call age buckets. So the age buckets are relative to today. So age buckets are relative to the time when the transformation, when the ETL is taking place. And this allows our customers to do those queries like how much data has been accessed in last 3 months, or how much data has not been accessed since last 6 months or so. So we are doing, as you can see, we are doing some aggregation as well. So we are getting the total count. So now it's saying that for first combination on share 1 in last 1 month for file type Word, we have got 2 items and total 180 KB size. And then the next one, it's saying that for between last month and last year for Excel, we have got 3 items with total 1000 KB size. So this is the aggregation part. So with that summarization overview, let's talk about the schema, the intermediate summary schema. So as I said, intermediate summary is the column family, is the table that helps us achieve that daily transformation, helps us get this aggregated counts and size for given bucket combinations. So to start with, what exactly are my requirements for this intermediate summary table? So we need a schema that allows us to get the total count and size for various bucket combinations. And then we want to have a schema where we can do insert and updates or any operations on the table in an idempotent manner. We don't want to get into the complexities of if error occurs, how do we clean up, how do we do manual roll-ups, rollbacks, things like that. So we want mechanism for idempotent operations. And one of the key thing is we want to have a schema where we could relatively quickly iterate through all the rows belonging to a container. So container in the context of our application is a share on a file server. And because of the way various modules in our application work, they use this container as its logical unit of operation. So we want a mechanism by which we could enumerate all the items belonging to a share in relatively quick manner. So with that requirement, the first obvious thing that comes to mind is to use counters, because we want to get aggregated count and size. So use counters. But counters won't help us because the counters are not idempotent. So at least pre-Cassandra 2.1, I haven't used 2.1 counters, but at least pre-Cassandra 2.1, counters are not idempotent. And by that what I mean is, actually whenever you do any mutation in Cassandra, you can get write timeout errors. And in that case, you can't really say with certainty whether the underlying mutation completed on all the nodes all the replica nodes involved for that mutation or not. So now if that is a counter mutation, you get a write timeout error, you can't reliably retry your operation, because if you retry it and if it completed on some replica nodes last time, then you run the risk of over incrementing, or vice versa when you are decrementing. So obviously because of this problem, counters can give this discrepancy in aggregated count and size. We don't want that. So we have to think of something different, and we made use of collection data type map. So as you know, Cassandra allows you to have collection data types, maps, sets and lists, and map in this case helps us achieve idempotent operations, because if you get write timeout error, you could still safely retry the operation, because if it wasn't done last time, then you would do it, and if it was done, then you are just overwriting what was already there. So you still end up with the data that you wanted to be in your map. So from that point of view, map is good. So with that, the first schema that we came up was this kind of thing. So now we have got a primary key with container ID and rest of the buckets against which we want to get the total count and size. So this is my primary key, and the only other column in this table is map column, which is keyed with the item ID, and as a value we are storing the size for that item. So you can see that this is a compound primary key, and in Cassandra, when you have a compound primary key, the first column of your primary key acts as your partition key. So for those who are new to Cassandra, partition key is the one that decides where your data will be stored. So in your primary key, in this case, we have got container ID as our partition key, and rest of the columns in my primary key are clustering columns. So they decide the clustering order. So for this container ID, all the data for this container ID will be stored as one big internal row, and rest of the columns decide the order in which this data will be stored for that internal row. So with this scheme, now you can see that we could enumerate all the data for a container, because obviously we can do partition key lookup using container. And because of the clustering key order, because the data is sorted using these buckets, item type, size bucket, owner bucket and all the date buckets, so I can do slice range queries on that bucket if I want to. But there is problem with this schema. This diagram is just showing how it's kind of like a logical representation of how data will be stored. So it's saying that for a given container, all the data will be stored as one big internal row, and that's where the problem is. So now for a container, because we are storing the entire data for that container, all the items for various bucket combinations of that container will be stored as one big internal row. So this is of course a wide row because we are using compound primary key, but we are getting excessively wide rows because we will be ending up storing too much data for a given container as one internal row. And one of the main problem here is that the data distribution is not uniform. So I could easily have a container with very large number of items in it, and then there could be other containers with relatively less number of items in it. So the distribution of data is not really uniform, which is not good for Cassandra and leads to what is called hotspots. So some of the internal rows are excessively big, and that's not going to help us. So obviously we had to think of something better than that. So we looked at all our bucket combinations, and we realized that we have got two buckets, item type bucket and size bucket, for which we know the values in advance. So they have fixed range values and we know what the possible values can be. So we combined item type and size bucket with the container, and now that becomes my partition key. So if you see, what I'm doing in this approach is comparing it with the previous diagram. Instead of storing everything for that container as one big fat very wide row, now my internal row is based on container ID and item type and size bucket combination. So all the data belonging to a given value of container, item type and size bucket is now stored as one internal row, one physical row. So now I've controlled the excessive wide rows to some extent, and because we have got in mix item type and size bucket as the partition key, so now the data distribution is bit more uniform. So now we haven't got that hotspot problem that we were seeing with just container ID as the partition key. So now to enumerate, because we have to enumerate all the items for a container for our ETL, how would we do that? So we know the container at hand, and let's say we have 50 possible values for item type and 10 possible values for size buckets. So we have maximum 500 combinations. So we'll start with that container ID, and then for those we'll do 500 lookups in this example. So that allows me to go get all the partition keys for a given container, and then for each lookup we'll page through all the logical rows for that partition key. So by the way, DataStax Java driver gives you this seamless paging. So for a given combination of container, item type and size bucket, I can use that seamless paging from the DataStax Java driver. So all you have to do is at the time of your query you say what is the fetch size. So let's say the fetch size is 5000. Then for each partition key lookup, I can start enumerating my logical rows for that partition key in pages of 5000, and Java driver will take the responsibility of getting first 5000, and then once that is exhausted it will go to the server, get next 5000. So by that mechanism we can enumerate all the rows for the container. But if you look at the schema, we haven't really solved the hotspot problem, because all we have done is by combining item type and size bucket with the container ID, we have just reduced the chances of things not being uniform. But we could still end up in a scenario where we could have too much data for a given, too much items belonging to a given combination of item type and size bucket. Like on a specific file server on a share, you could have most of the file, or maybe 95% of the files of type Word and just in one size bucket boundary. So that hotspot problem is not really fully solved. So to solve that problem, we came up with this concept of salt. And again, the idea is salt has got a fixed range of values, let's say from 1 to 50. And we generate this salt by hashing some of the attributes of items. So some of the item metadata properties, we hash that, and we divide that hash value by 50, and whatever is the remainder, that becomes my salt. So by adding salt into the partition key, what we have done now is, first of all, we have again reduced the wide rows to some extent, and then the next important thing that we have done is we have taken more control over the data distribution, because the salt is something that is not just based on the type bucket and size bucket, but it's based on other properties of the item. And these properties are, for example, file name, extension, the exact size of that file, and one of the date. So by having all those things mixed into the salt and hence into the partition key, now we can control the distribution of data a bit better. So with that, we are controlling the hotspot problem in a better way. So that worked for us for some time, but then after some time we started seeing a lot of read timeout errors. And we looked into it. We use Node tool. So as many of you know, Node tool is an excellent tool to get to know about your cluster and look at various, if you are troubleshooting, get various information about cluster. It comes with so many options. CF histogram is one such option, column family histogram. And what this does is it provides you with read and write latency, and it also gives you a histogram of reads and the number of SS tables involved in fulfilling that reads. So we use that particular bit, and we realized that in our case, for very large number of reads, large number of SS tables were being used. More than 10 SS tables were being used, which is not good. So we found out that it's because of the updates. So when an update occurs, your row may be fragmented into multiple SS tables, and when you are reading such row, now Cassandra has to go to all those SS tables, get the row back. So it's involved, when it is involved reading multiple SS tables, then it affects your read latency, and hence you can get read timeouts. So to solve that problem, we looked at our compaction strategy, and Cassandra by default gives you size tier compaction strategy. And without going into much details, basically what size tier is saying is, when there are enough SS tables of similar size, they will be compacted into a bigger SS table. So size tier is good for scenarios where you are doing lots of writes and then you are doing reads and there are either no updates or less updates to that partition key. So because we had lots of updates, so obviously size tier was not helping in our ETL process. So we looked at other compaction strategy, leveled compaction strategy. And in leveled compaction strategy, what you have is you have fixed size SS tables which are grouped into levels. And each following level is 10 times the size of the previous level. So if you have 10 in level 1, if you have 10 SS tables in level 1, you have 100 and so on in level 2. And the way leveled compaction algorithm works is it tries to ensure that there aren't any overlapping SS tables in the same level. So with that, it can give you a guarantee that 90% of the reads will be satisfied from just one SS table. And because it has to give that guarantee, it's more IO intensive. So we changed that compaction strategy for just intermediate summary table in our application, left others on size tier. And we tested it and we found that the ingest rate was not impacted a lot. And we definitely saw improvements in our ETL, so we were not seeing those many read time out errors. And we again used node tool histogram, and this time we found that obviously the number of SS tables required for the reads had reduced. So when earlier we were seeing large number of them needing 10 or more SS tables, we had only 2 SS tables, most of them through one and only 2 or 3 for some reads. So that was useful. Then the next thing is the issue with collections or our usage of collection. So as mentioned earlier, we had primary key and then the only non-key column is map, which is a collection data type which has got item ID and size as the value. So there are certain problems with that usage, and one problem is that collections are read in its entirety. So for a given primary key in my map, if I have, let's say, just 1000 items or 50,000 items belonging to that bucket, when I'm reading that row, it will all be read in its entirety. So maps or all those collection types are read in its entirety. So what it means for us is, because we are navigating in pages for a given partition key, so let's say we are navigating in pages of 5,000, so we expect to get 5,000 rows. But then each of these 5,000 rows, which is like a unique bucket combination in our case, has got a map associated with it, and that map can have variable amount of data. So some can have, let's say, 1,000, others could have 50,000. So basically, even though we are getting fixed number of rows, we are still getting back a variable amount of data, in some cases a very large amount of data. So that's not good. And then the second problem is collections can have only 64,000 entries. So we knew from our usage that we could end up with one bucket combination needing to have more than 64,000 items stored against it. So obviously that was not good for us. So we had to look back at our schema and come up with something different. So what we did this time was we removed the map, and because the map was keyed with item ID, so now we have got item ID as part of the primary key. So item ID is the last clustering column in my primary key, and now the only non-key column in this table is size for that item. So if you think about this, even with this schema, I am virtually achieving the same thing that I had with the previous schema, where I had a primary key for a bucket combination and then map stored against it telling me how many items belong to that bucket combination. Now I have got this primary key with item ID as the last clustering column and the size. So now if I want to get the total count and size for a given bucket combination, I can use the same thing. I will start enumerating, and because everything is ordered by the clustering column, so for a given value of container, size, item type and salt, everything is sorted by rest of the columns in the primary key, which is owner and the date buckets. So now till I get the same value for owner and the date buckets, I can keep on aggregating, because that is going to tell me that all these items belong to the same bucket combination. So I can keep aggregating the count and the total size, and as soon as that any value in the combination changes, I know that I've moved from one bucket to another bucket. So that was something we had to change in our client side to get that same aggregation that we were earlier getting through map, but that change was trivial. So we did that, and with that change, now we don't have the limitations of collection data type anymore. So that worked for some time, but we again started hitting issues and again started getting read timeout errors. So we looked a bit more into it to understand what's going on, and what we found was we were getting errors in Cassandra system log, and these errors were saying that it has hit more than 100,000 tombstones for a given slice range query. So as mentioned earlier, because of this ETL enumeration, we are enumerating in pages, which translates to a slice range query in Cassandra terms for that partition key. And what this error was saying was, within a particular slice range, again let's say we are enumerating in page size of 5,000. So for those 5,000 rows, Cassandra had hit more than 100,000 tombstones for just 5,000 active rows, and that was causing Cassandra to abort the query. So these values, the threshold at which this query is aborted, we have got two settings. One is where Cassandra gives the warning, which is by default 1,000. So if it hits 1,000 tombstones in that range, in the slice range query, it gives a warning in the system.log, and if it hits more than 100,000, then it throws an error. So we could have controlled it by increasing this threshold, which says after how many tombstones you want to throw the error, but obviously that's not a good idea, because if you think about why Cassandra has to do this, when it is enumerating, when it is going through that query, when it is going through your slice range query, the reason it has to basically it has to return not just the active data, but it has to also return any tombstone that it found in that range to the coordinator, because it is up to the coordinator to take the decision whether that data is really deleted or it has got some other node, other replica saying that I have got another data with higher timestamp, in that case this data is not really deleted. So that reconciliation is done at the coordinator node. So for that reason, any tombstones encountered within a given slice range have to be returned to the coordinator node. So if we just increase this value, we run the risk of returning too much data to the coordinator node and putting a lot of stress on the coordinator node, which is obviously not good. So we looked at something else. So this is the GC grace seconds setting, and as many of you know, this setting basically what it is saying is for how long these tombstones will be stored in the SS table. So as we know, tombstone is just a marker for the deleted record, and the duration for which this marker, this tombstone, will be stored in SS tables is controlled by this setting GC grace seconds, and by default it is equivalent to 10 days. So for our usage, what we did was we changed that value from 10 to 5, so that the tombstones in intermediate summary table are evicted sooner. But in doing that, we had to look at our repair process, because what happens in Cassandra is, in order to ensure that your deleted data doesn't reappears back, you have to repair all the nodes in your cluster, and it should be done in a way so that repair for all the nodes completes at least once in the window which is less than GC grace seconds. So if GC grace second is left to the default value of 10 days, then you have to make sure that all the nodes in the cluster are repaired at least once in that 10-day duration, because the thing is, if you don't do that, and let's say we have got two nodes, one knows it has got the tombstone, and this for whatever reason missed the delete, then if this node is not told about the delete in less than 10 days, then once the tombstone are evicted from this node, all of a sudden when you do the read again, this might say, I've got the data, so the deleted data may reappear back. So for that reason, we have to do the repair. Node tool repair is done as part of your background maintenance job. So we already had a repaired script to to repair all our tables, which we were aiming to do once every 10 days. But now because of that change, we had to make that repair bit different. So we had to have one script just to repair intermediate summary. So we set it to run every 3 days so that it gets repaired in a window less than 5 days. And the other script was now repairing rest of the tables, so all the tables but intermediate summary tables. So the node tool repair, you could do it either the entire node or by key space or by a specific table in the key space. So we started doing it for all the tables but intermediate summary in the other script. That was done in a way so that they get repaired at least once in 10 days. So that's how we managed this Tombstone, the deletion issue. But then we looked at our schema a bit more, and we wanted to understand why we had so many deletes. And if you look at the schema, this particular table has got everything as its primary key other than the size. So what it really means is, if any attribute of the item changes and item moves from one bucket to another, you can't really do an update because it's the primary key. So that update, that logical business update of the item meant that we had to do a delete and then an insert again into this table, which means we were actually doing lots of deletes for the updates, which were not actually the logical deletes, which were not the business operation deletes. So those updates, business operation updates, meant more deletes for us. So we looked again at all our buckets and we looked at the various item properties, and we realized that dates are the attributes that change most frequently. So we took the dates out of the primary key, like modified date access dates. They are the ones that are going to be changed most frequently. So we took them out of the primary key and that made them non-key column, which meant that if those values change and items move from one bucket to another, we can do the update inline and we don't end up deleting and reinserting and hence creating more tombstones. But the disadvantage in this approach is, now I can no longer rely on the clustering columns sort order that I mentioned earlier, because dates are no longer part of the primary key, so I can't rely on the clustering order. So just the act of getting the aggregated count and aggregated size for a given bucket combination is slightly more involved. So what we had to do now was, we had to cache everything that for that, I mean we could have just used owner ID as well, but we just cached everything for the partition key for a given combination of size, item type and salt. And for that in-memory cache, we would have different bucket combinations which we were managing in memory, and for each bucket combination we were getting in memory the aggregated count and aggregated size. So again, by this means we were still able to achieve what we wanted to do, but we were able to control the deletes to some extent. So that's pretty much it. Any questions?
My question is regarding, you mentioned several times you changed the schema. How do you go about doing that? Is there a process to reload the existing data into the new schema that you had or utilized?
Yeah, so actually that's a very good point. We were lucky that most of the primary key changes were either in the alpha version of our data or beta duration. So actually we were not, so for the changes where we had to pretty much like rebuild the table, we had the luxury, we were lucky that we had the luxury to start from scratch. So that was easy. The last thing that I talked about, that's something that we have to do on the production cluster. And that's why actually it's still not rolled out to the production cluster. And what we have is got a process where we would be managing writing to two tables, the old table and the new table, through our application at the same time. And we will have a mechanism by which we will know when to do this switchover. Because we will know as part of our ETL process, we will know once everything is done, all the old data is done, and that's how we will be managing this switchover. So yeah, all that complexity will be in our application so that we keep on writing to the old and the new table, and once the data has been migrated, so we'll have a process that will be migrating. So this is all we are working right now. So that will be migrating the data from the old to the new table, and once all that migration is done in our application, we'll switch it so that it only writes to the new table this time.
So you had an aging out process of the old data from the old tables.
Yeah.
Okay,
Yeah.
thank you.
You mentioned it would be, you have to have about 500 loops in order to get the data before the salt.
Yeah.
Then you added 50 more. Does that mean you have 25,000?
Correct. Yeah. So yes, so there is definitely a disadvantage in this approach. And as you pointed out, the disadvantage is now we are doing, in this case, 2,500 lookups. And the disadvantage is basically in those cases where some of the lookups may not have any data. So that's exactly what we have worked now. So I think this is something that has gone live in production, I think last week. And that's actually a topic for discussion some other day. But in brief, what we are doing is, in another column family, we are keeping tracks of how many out of those 2,500 combinations really have got the data. So this is done in a way, as I mentioned, in our ingest workflow for any combinations. And this time we are able to use sets because we know what the limit is, what the upper bound is. So we are using, for a given container, we are using a set that will have all the combinations that really have data. And because we know that these combinations cannot get more than 64,000, so we are safe to use the set. And that combinations will be kept in sync. So new entries or any inserts will happen at the ingest time. And when our ETL finds a combination which is empty, it removes that record from the set. So it is like kind of self-healing itself. So through that mechanism, we can avoid those empty lookups.
We actually are out of time.
Sorry, if you have any questions, we can discuss offline. Thank you.